So you've been given a question where you have to find two numbers to add up to a number, and their product is maximized. Now, to identify these two numbers, you must understand that this question has to do with optimization. Now, optimization, in very basic words, is taking what you got and doing the best with it. So it's basically the measure of efficiency. So, anytime you see maximized or minimized, it's basically an optimization problem. Now let's see how to do this. So how do we even go about this? Well, the first step to any optimization problem is to identify the constraint. And those constraints sometimes make their own equations. For example, over here, our constraint is that the two numbers have to add up to 400. So I'm going to call my two numbers x and y, and x plus y is 400. Alright. Now how about the product? Well, the product is maximized, right? So x times y is what? Now, I'm going to call this variable m because it's maximized product. So might as well call it m. You can call it anything as long as they don't tell you what to call it. But this doesn't really matter. The reason is, my thought process here is I have to find where it's maximized or minimized. We don't know that yet. To do that, we can use the power of derivatives. Now, if you remember, derivatives can tell us critical points, and maximization and minimization are basically critical points. And with the help of the second derivative, if the second derivative is negative, which indicates concave down, we know that the critical point is going to be maximized, or the max, right? So, what we want is dm over dx or dy. You can choose any. That's something that you can pick. Dm over dx is 0, and d squared m over dx squared, which indicates second derivative, is negative something, negative n. Okay? Now, notice we have two variables, and if we take the derivative right now, we'll have a dy over dx, which is not something that we can solve, right? We don't want a dy over dx. All we need is x, something that's solvable. Okay? So how do we do that? Well, that's where our constraint comes in. This is our constraint equation. If we do substitution, x equals 400 minus y, or y equals 400 minus x, either one. If you're substituting for x, you choose this one. If you're substituting for y, you choose this one. But here I'm substituting for y, so I'm going to choose the second. Okay. So, what I'm going to do is rewrite my equation. X times 400 minus x equals m. Now, if you look at this, we only have two variables now. Now, this becomes solvable. Okay, so what I'm going to do here is I'm going to take the derivative, but before I do that, I'm going to multiply this out because it's much faster. So, let's call this 400x minus x squared equals m, and dm over dx equals basic power rule minus 2x. Now, this is equal to 0. Alright? So, all we have to do is solve for x. And from this, you can see that x equals 200. And that's our answer. That's literally our answer. But I skipped a step here. I did not confirm if this minimizes or maximizes the area. So to do that, we have to take the second derivative. Okay? Okay, so when I take the second derivative, (400 minus 2x), right? So that's going to become -2. Alright? So for any value of x, we're getting -2 as the answer. And if it's -2, that means the graph is concave down like this. That means our max is the vertex. So we can only find the max, you can't find the minimum. So the critical point we found is the maximum. So as x equals 200, we get our product that is maximized. But we only found x, so how about y? Well, we take this x and we put it in this equation here. So all we have to do is 400 minus 200, which equals y, and y is also equal to 200. So those are our two numbers. Y is 200, x is 200. Now if you notice something, we just made a square. When you're multiplying, you do 200 times 200, which is basically the same number for each of the variables, which is always the solution when it comes to a question like this. So this is our last and final problem for today, and it's a very common problem for optimization. We're going to have a part 2 video where we're going to have more problems that have to do with optimization. But this one deals with you trying to design a box that maximizes volume by finding the appropriate height. So you have a cardboard sheet, right? A 24 by 12 cardboard sheet. Now to make a box, you're cutting off these square corners, right? And those square corners will help you fold these sides up, which will make you have a height of x, right? For that open box, I would say it has no top. So forget about the top. So it's more like a tray. So to maximize the volume, you have to figure out what that height is, right? You have to figure out x, okay? And that's our constraint. Our constraint is the height of x, and sorry, our constraint is the dimensions that are given to this rectangle. And we're trying to find the height based on those constraints. So I have the dimensions, and we're going to find the volume using the volume equation, which is length times width times height. So I'm going to do x, which is the height, times 24. But that's not our length now, because we're cutting that same amount both sides, right? We're cutting x on both sides. So that's going to be 24 minus 2x. And we're also cutting two sides on 12. So our other, our width is going to be 12 minus 2x. And now I have to take the derivative and find the maximum. And that's what takes the longest about this problem. So with the calculator, you could do this instantly. It's just that calculus is meant to be done without a calculator. It's basically the math that teaches calculators how to work, right? So let's try to do this without a calculator. To do that, we're going to take the derivative of this. But first, I'm thinking, should I expand? And I think I really want to expand here. The reason is, if I were to do the product rule, I have to do more expansion problems, which is going to take a lot of time. So I'm going to expand right here. So instead of doing this immediately, what I'm going to do is I'm going to go with v equals 24x minus 2x squared, and I'm going to multiply that out, right? I'm going to multiply that out. So our new volume, or our expanded volume, is going to be 288x minus, let's do 2 times 12 minus 24x squared. And now these two minus 48x squared. And what we're going to do last is these two. Excuse me, plus 4x to the third. Alright, so that is our final equation, right? Let me just make sure I did everything right. Don't see anything wrong right now. And finally, we're going to take the derivative, right? dv over dx. And that's going to be equal to 0. So, our derivative is going to be 288 minus, if we combine like terms, it's going to be 144x plus 3 times 4, that's 12x to the second. And now I want to solve for x when dv over dx is 0. So, and keep in mind, since it's a quadratic, we're going to get two answers. And I'll show you how to see which one it is, because it's far more complicated than just plugging it into the second derivative, which we're going to do. So here, I'm going to factor out a 12 from all of this. So 12 times x squared minus, that's going to be 12x plus 24, right? And I'm going to divide the 12 both sides, because I really do not care about this quadratic. So what I'm going to do here instead is basically go for the quadratic formula, because this is not factorable. And having no 12 helps us speed up the calculation, because we're factoring out a 12 from every single term. The math still checks out. So I'm going to say x equals negative 12 or negative 12, so that has to be 12 plus or minus square root of 144 minus 4 times 24. 4 times 24, that's going to be 96, all divided by, that's going to be 1. I'm going to say, yeah. Right? Okay. So, what we're going to have here is 144 minus 96. X equals, okay. So, that's going to be 48. 12 plus or minus square root of 48. And I'm just going to take a 4 out. I could take a 16 out. So I could do 12 plus or minus 16 times 3 is 48. So I'm going to do 4 square root of 3. And that's our answer. But we are not done yet. So we have x that could equal 12 plus 4 square root of 3 or 12 minus 4 square root of 3. Now, how do we know which one to use? Well, that's where our next derivative comes in. The second derivative, d squared v over dx squared, equals, okay, let's go up. Now we have to use the full quadratic. So that's going to be 24x minus 144. Okay. Now we have to plug in a number. to plug in that number, we have to understand that the one you pick has to be less than 144. The product has to be less than 144. And 24 times, let's see, 24 times 6 is 144. Okay? So 24 times 6 is 144. Okay. Now it's really hard to calculate this without a calculator if we were to plainly plug this in. But using this logic of 24 times 6 equaling 144, anything less than 6 in this product is going to give us a negative number. And that's what we want. So if you look at this, 12 plus 4 square root of 3 is going to be a positive number, which is greater than 6. But 12 minus 4 square root of 3 is definitely going to be less than 6. At least I can assume that because this is the only number I have remaining, and that's going to be less than 12 itself, so it most likely is less than 6. And to verify this, I can also say that square root of 3 is approximately 1.7-ish. So 4 times 1.7 is definitely greater than 6. So it's going to be, definitely greater than 6. So if I were to subtract 12 minus that number, it's going to be less than 6, right, for the product. So our answer for the height, or x in other words, is going to be 12 minus 4 square root of 3. That's our answer. So calculus is basically creativity in mathematics. And there you have it. Optimization isn't that hard. Well, we're going to cover more examples in the next video. And until then, keep practicing.